This video is to help you understand how to use the multiplication rule, or the rule that applies to independent and dependent probability events. When we have independent events or dependent events, basically they talk about two events happening at the same time, such as the events at the bottom of the screen. If I'm going to draw a heart and then a spade, if I'm going to draw two cards from a deck of cards, the probability that I draw a heart and then a spade after replacing the heart means that that's going to be a couple of independent events, right? The first card is replaced and therefore doesn't affect the second card. The entire deck is still present when you try to draw that second card. And in that case, we can just say, well, the probability of drawing a heart is 13 out of 52, and the probability of drawing a spade, again, given that the heart is replaced, is still 13 out of 52. There are 13 spades and there are still 52 cards. So we just multiply those two events because that's the probability of one event happening and the other event happening. Again, that keyword being and. We're multiplying those two events, which means we'll get 1/4 times a quarter is a 16th, and basically 0.0625 chance of drawing a heart and then a spade. Now, if we don't replace that spade, or sorry, the heart the first time around, if we don't replace the first card, now that second card is affected by what happened the first time, or we call that a conditional event. The probability that B happens given that A already happened, or this B bar A, probability of B such that, again, A already happened, well, that's going to change the probability of that second event. Therefore, we call those dependent events. Okay? And the probability of A and B happening becomes the probability of A multiplied by the probability of B given that A, again, already happened. Well, how that changes things is that, again, the probability of drawing a heart is still 13 out of 52. That was still a full deck of cards. However, the probability of drawing a spade, given that there's a heart missing, given that one card is missing from the deck, well, there's still 13 spades, but there are only 51 cards left in the deck. So the probability of drawing a spade is actually a little bit greater, a little bit better, because there's not one other sort of distraction card still in there. So 13 over 52 times 13 over 51, we get a slightly better probability, because again, getting a spade is more likely given that there's only 51 cards versus getting it out of 52 cards. Again, that's the probability of dependent versus independent. So let's look at a couple more situations. A dependent event, again, happens when a probability of B is different from the probability of B given that something else happened. If that first event changes my next probability. So if you're drawing two marbles from a bag containing 3 red, 3 blue, and 2 yellow, again, if I draw two marbles and I don't replace without replacing the first marble, then what happens on the first marble is going to affect what happens in the next one. So the probability that both of them happen is that the probability of getting a red the first time times the probability of getting a red given that I already had a red the first time. Or basically it's 3/8. 3 out of the 8 marbles were red the first time around. But with a red marble already missing, now there's only 2 red marbles left out of the 7 remaining marbles. So again, 3/8 isn't multiplied again by itself. We didn't put the other red back. We multiply it by a new probability. The probability of red given there's a red one missing. If you multiply those out, you'll get your probability and you have your answer. Again, in the real world, where could you use this? Well, how about quality control? A quality control procedure for testing disposable cameras consists of drawing 2 cameras, one after the other, from a lot of 100. Only if both cameras are defective is the entire lot rejected. Well, we want to find the probability that we accept the lot, the probability that we have a good lot of cameras, which basically means the probability that they're not defective, the probability they're not rejected. Well, to find the probability of being rejected, we can do that in one of 2 ways. Again, we would only reject the lot if both cameras that we draw are defective. So one way to look at that is, well, there are 10 out of the 100 cameras that we know of, right? We said there's 10 defective cameras in that lot of 100. Probability of drawing the first one would be 10 out of 100 then. But again, assuming we don't put that defective one back, the probability of getting another defective camera is now only 9 out of 99. Another way to look at that is to say that we're going to draw 2 cameras out of the 10 defective ones. Doesn't matter the order in which we draw them in. So again, we're thinking about combinations, but 2 of them are going to be defective, and we're not going to draw any good cameras out of the chances that we draw 2 cameras out of the 100 to begin with. So what we want to have happen versus what could happen. Either way we look at it, we're going to get a probability of 0.0091. But now remember, that's the probability of being rejected. We wanted the probability of acceptance. So take 1 minus that, and we'll have our probability that we would accept that lot of cameras. Again, probably the best way to go. You don't want to just take the probability you draw 2 good cameras, because remember, we'd also have to worry about the probability of drawing 1 good one, and whether or not that one was the first one or the second one. There's just a lot of scenarios, at least 3 different scenarios we'd have to worry about if we've tried to go toward drawing good cameras. Much easier to say, well, the only time it's bad is if we reject, right? If both of them are bad, then we'll reject, and the opposite of that would be accept. The complement of that would be accept. Let's look at a couple of independent events. Again, independent events are where that first event doesn't affect the second one. The probability of B is the same. It's equal to probability of B given that A already happened. Things like rolling dice would be independent events. If I roll 2 dice, what's the probability of we roll a pair of 5s? Well, the probability of the first 5 is 1 out of 6. And what happens on the first dice in no way affects what's going to happen on the next. So the probability of a pair of 5s is just 1/6 times 1/6, or 136.0278. Again, the first dice in no way affects the second one. Another event that could happen, Mike is 55, Helen's 35. Maybe we're an actuary and we're trying to figure out an insurance plan for them. Their probabilities of dying individually are 0.28 and 0.028, whatever their age, their lifestyle, whatever is going into this. Well, again, we've kind of calculated their probability, according to what we know, of dying. Well, if their lifespan of one has no effect on the other, if they don't know each other, they live in totally different places, what's the probability that they will both be alive in 10 years? Well, if they don't affect one another, then they are independent events. Again, them dying would be independent events. So, if we want the probability again that they're going to be alive in 10 years, the first thing we're going to want to do is figure out, well, if 28% is the probability that Mike is dying, then 72% is the chance he's still alive. Same thing goes for Helen. There's a 92% chance that she's still going to be alive. And if we take those 2 probabilities of being alive and we multiply them, again, the probability of Mike and Helen both being alive then, multiply the 2 events, is 0.6628. Again, I hope that helps you when you're talking about independent versus dependent compound events. We're talking about that word and. Remember, that's the key. That's the reason we're multiplying, to try to find the total probability that both things could happen at the same time. 2 events happening at the same time. Again, if you have any questions, make sure you talk to your teacher. Otherwise, good luck and happy counting.